So having spent some time yesterday talking about equilibrium properties of hot n equals 4 super Yang-Mills and how to extract them in the strong coupling regime using gauge string duality, today I want to start talking about certain non-equilibrium or at least real-time phenomena that are physically interesting and show you some examples of how to calculate them, again using gauge string duality. Before I start, I actually want to remind you of a little bit of, basic quantum mechanics, response functions and some of the relations between response functions that are going to be relevant for a number of the applications I want to talk about. So imagine you have any quantum system. Imagine you change the Hamiltonian by adding some perturbation, generically some time-dependent perturbation to it. And I'll say that I have one or more operators. I'm calling them capital A. And I'm multiplying them by some arbitrary functions that are on my control. So this is a perturbation to the Hamiltonian that's going to change the resulting time evolution, and that's, of course, going to change resulting expectation values. And in particular, suppose I want to measure the change in the expectation value of one of the operators that happens to be one of the same operators that I'm perturbing the Hamiltonian with. A classic result in first-order time-dependent perturbation theory, let's call this C, is to show that the perturbation or the response to the perturbation is related to the strength of those perturbations that I turned on by a response function which is nothing other than a retarded correlator. So the capital R is just a reminder for retarded. And this correlation function you're now supposed to evaluate in the unperturbed theory where you didn't have this perturbation turned on. OK, like any two-point correlation function, this retarded correlator, if you Fourier transform it, and I'm going to write time components separate from space components. So as a function of frequency and a wave vector, like any two-point function, you can write a spectral representation that will express this correlation function in terms of what's called a spectral density. And this is just an integral representation of this form. And that's useful because exactly the same spectral density contains the information that you need to reconstruct other two-point correlation functions, such as, for example, the Euclidean correlator, which, since at finite temperature, the Euclidean time variable is periodic, as we've seen. When you Fourier transform it, its Fourier transform only depends on some set of discrete Matsubara frequencies, but this satisfies a spectral representation that looks almost exactly the same except in the denominator, instead of having the difference of two real frequencies in an I epsilon prescription, you have I times a Matsubara frequency. And the one other example of this I want to put up here, because I'm going to use it, is something that's even simpler. So this is Euclidean. What's sometimes called a Whiteman correlator is a name just for an expectation value of a product of these two operators, but without any time ordering. So this is not the time-ordered correlator. It's not the retarded correlator. It's simply the expectation value of the product of these operators, regardless of whether the time at which this operator acts is before or after the time at which that operator acts. Right? If you Fourier transform that correlator, in fact, the result is exactly the same as the spectral density multiplied by a simple function in front, which is just the usual Bose distribution function. Okay. There are lots and lots of applications of this, a few of which I pre-prepared here. So, for example, if you have some system and you want to turn on an external electric field that couples to the current density of whatever your dynamical charges are in the theory, and you can think of that in exactly the same language I have up above, where the operators that you're coupling to are the electromagnetic current density, the external field is your chosen electric field. Right? So asking for this linear response in this example is the same thing as asking for the relation between the induced current and the electric field, and the conventional name for what appears there is the electric conductivity. So you apply the same setup we have above there. You write the response in terms of this correlator. Out comes a formula for the conductivity. You can express it in several different ways. What I wrote here is one conventional way of writing it. This is called a Kubo formula. And it gives you the conductivity in terms of, well, I've chosen to write this in terms of this last Whiteman correlator. So you take simply the expectation of the product of your electromagnetic currents in equilibrium. You Fourier transform it. You evaluate it at zero wave vector, and you take the limit as frequency goes to 0, and up to some overall prefactor that is a valid representation for the conductivity.
Can you explain why you use Whiteman correlator?
Well, as these relations above show, you can rewrite it completely correctly in equivalent form. So this happens to be one valid form. I could have equivalently written it in terms of the spectral density divided by omega, because this Bose distribution function for small frequency just behaves like temperature divided by frequency. Or you could look at the formula for the retarded correlator up above, and you'll notice that if you take the imaginary part, the spectral density is directly related to the imaginary part of the retarded correlator, so you could write the same formula in terms of the imaginary part of the retarded correlator. They're all equivalent. Frankly, I picked this one because it's easy to write and you don't see any extra factors of 1 over omega. I do want to point out that this formula, which is the one you'll find in most textbooks, tells you to set this wave number to 0 first and then send the frequency to 0, and that's perfectly fine. That's also not unique. An equally valid form is to actually Fourier transform the current correlator and evaluate it on the light cone for null 4 momenta, and then take the limit as that light cone momentum goes to 0. And the only difference is it changes the prefactor. All right, if you're thinking about diffusion, it's the same story over again. If you have some set of locally conserved charge densities that think of as being flavor charges, a diffusion constant is something that relates gradient and charge densities to fluxes of those conserved currents. If you have multiple, I actually wrote this wrong, if you have multiple conserved currents in general, you can have a matrix of diffusion constants. And here's a Kubo formula for that matrix of diffusion constants, except what I didn't write here is there's a factor on the right-hand side, which is I also didn't have this quite right. There's a matrix of charge susceptibilities there. Okay. I just want to show a couple other examples. Here's the same thing for viscosity. If you have any system that has hydrodynamic fluctuations, if you look at small displacements from equilibrium, well, first I should say in equilibrium, the expectation value of the stress tensor is just diagonal equal to the pressure times the identity matrix. There are corrections to that if you have fluctuations, and in particular, if you have a system in which there's gradients of the fluid velocity, then there are corrections to the stress tensor proportional to gradients of that velocity. And for the traceless part of the stress tensor, the coefficient is what is called shear viscosity. And again, the same story applying this linear response function. Formalism gives you a formula for that shear viscosity in terms of a traceless stress correlator. Okay, I want to write one other one. I didn't have time to pre-prepare. Suppose I have a system which I'm really thinking of as being something like a quark gluon plasma, but suppose I now turn on electromagnetism. So in addition to the strong dynamics of all the degrees of freedom in this box, we also have some electromagnetically charged particles. They're going to get bounced around, they're going to jostle, they're going to radiate photons, but the electromagnetic coupling is very weak. So photons that get emitted from somewhere inside that box, if the electromagnetic coupling is sufficiently weak, will have a negligible probability of being rescattered on their way out of the box and will escape. All right, so formally that makes sense. And experimentally, it's actually relevant. Real heavy ion collisions are, roughly similar to this caricature. You have a little blob of hot, dense, strongly interacting stuff. And if photons are produced somewhere in the middle of that little ball of hot plasma, the photon attenuation length should be much larger than the size of that little ball. So photons are probes which will actually escape and are experimentally quite interesting as a result. Okay, well, I already said that by assumption, I'm treating the electromagnetic coupling as being very weak. So turning on the coupling between an external, between the electromagnetic gauge field and my charge degrees of freedom running around in my box is yet another application of the same sort of perturbation theory. And so if you ask what is the spectrum of photons which will be emitted, well, you can ask for the rate at which photons are emitted in some little volume in photon momentum space, so there'll be a d3k divided by 2 pi's. Twice the photon energy makes this a nice Lorentz covariant volume element. And what makes this a correct formula is precisely the Whiteman correlator I was just discussing, evaluated at on-shell momenta for the photons, where this is specifically the Whiteman correlator of the electromagnetic current. Okay, and a final example, which I won't write out in any detail, is dilepton emission. If you think about how you produce pairs, mu mu bar, for example, dileptons coming out, it can be exactly the same picture, except instead of turning into a real photon, you have a virtual photon, which is off shell, that turns into a dilepton pair. And so there's a completely analogous formula. And all I want to say about it is it once again involves exactly the same correlation function, but now evaluated not at a light-like four momenta, but at the total four momentum of that dilepton pair. Okay, so for actual applications to heavy ion collisions, viscosity is certainly relevant, and there's been a lot of discussion of how the data, how an enormous mountain of data that's come out of doing relativistic heavy ion collisions all supports a picture that this hot quark gluon plasma is behaving like a nearly ideal fluid with very low viscosity. An interesting question is to sort of make that crisp. How good are the limits that you can put on the viscosity from the data, and what do we predict from theory? What should the viscosity of a quark gluon plasma be? So on the theory side, understanding how to calculate the viscosity for a strongly interacting quark gluon plasma is obviously interesting. Similarly, understanding what spectrum of photons you expect to be emitted is, again, of direct experimental interest and is something we'd like to understand how to calculate. And one of the things I hope is obvious is how you get a lot of output for the effort of calculating exactly the same two-point correlation functions of things like the electromagnetic current or stress tensor. So for my lecture today, I wanted to just pick one of these examples, and the example I'm going to focus on is just calculating that current-current correlator for the electromagnetic currents, all right, from which one can get the photoemission spectrum, the electrical conductivity, and dilepton production. Okay. Well, how do we do it? You've already heard the basic setup for extracting expectation values of local operators using ADS-CFT duality, right? And it all begins by saying think about turning on some external source which is going to couple to that operator. Really think about a generating functional for correlation functions of this operator of interest. And under the duality, this is going to translate into some prescription that says solve string theory on the appropriate gravitational background, but with now prescribed boundary behavior of certain fields that are directly related to the sources that you wanted to turn on in your generating functional. All that framework fits perfectly with this particular application, right? I want to get out a correlation function of the electromagnetic current. The appropriate source to turn on is precisely a background electromagnetic gauge field. For the purpose of calculating that correlation function, I'm perfectly free to think of this as a non-dynamical gauge field. So I don't really have to think about quantum electrodynamics at all. I just have some given background U1 gauge field. And because I want to use capital A mu's for something else later, I'm going to call it little a mu. All right, so this is going to be the source. It's going to couple to the electromagnetic current. And therefore, under our gauge string duality, this is going to be the boundary value of the bulk field, which in a sense is dual, well, boundary value of bulk field, dual to our operator of interest, which is going to be electromagnetic current. What is that? Well, we're going to have to discuss exactly what we mean by the electromagnetic current in the theory in which we're actually doing this calculation. I'll come to that in just a second. But the bottom line is simple. In the large NC, large lambda limit, the low energy degrees of freedom on the gravitational side are precisely the fields in supergravity. And one of those bulk fields is just a perfectly ordinary gauge field. And so we're going to have a bulk gauge field. And as I'll talk about in just a second, it'll be a bulk U1 gauge field. There are a lot more than a single bulk U1 gauge field in supergravity that's relevant for understanding n equals 4 super Yang-Mills. This will be a particular U1 subgroup of the full SO6 or SU4 non-abelian gauge field. Okay, I'll firm that up in just a second. But let me now just put up what is really the same version of what you saw in the last lecture and what I just said in words. All right, so this generating functional is now supposed to be given by some 5-dimensional description. Well, really, I should write here some 10-dimensional description because we're really working on ADS5 cross S5. But the S5 part isn't going to play any interesting role in anything I say today. So really, the only thing that's significant is the ADS5 part of that description. And in the lambda and large NC limit, this is nothing other than an exponential of the supergravity action evaluated on shell in the ADS black hole background, but with the particular bulk field that's going to be special now having prescribed behavior at the boundary. So in the coordinates I'm using, the boundary is at u equals 0. So the source that appears here in my generating functional is now just that boundary value. Good. Okay, so what is the supergravity action? Again, in principle, I should start with 10-dimensional supergravity. I should think about all the fields that appear. Since nothing interesting is going to be happening from the S5, I'm going to write down a version reduced to just the 5-dimensional ADS black hole spacetime. And the only thing the S5 does is give you a factor out in front, which is essentially the volume of that S5 that conspires into giving you the particular factors out in front, which I'm writing here. So this is, if you will, the 5-dimensional Newton constant, but expressed in field theory terms, which is what I'm going to use exclusively. So NC is the usual NC. L is my name for the curvature radius that we've seen before. OK, what do we have? We have the usual gravitational or Ricci scalar term. There's a dilaton, and there is the usual field strength squared term for the, well, we'll write it as an SU4 gauge field. And then what have I not written? There's terms with fermions. There's terms with interactions. Since the only thing I'm going to worry about today is calculating a 2-point correlation function, the only thing that's going to be relevant for me is terms that are quadratic in this action. So I'm going to completely forget about all the dots. Fermions won't play any role. In fact, the dilaton won't play any role. And everything I'm saying today is really going to be focused on thinking about this piece of the action. OK, this is really an SU4 gauge field. I want to calculate electromagnetic current correlators. And that's meaningless until we decide how do you couple electromagnetism to this theory. Well, I want to turn on an external U1 gauge field. It better be coupled to a conserved current. We have a perfectly nice set of conserved currents in n equals 4 super Yang-Mills, which are the R-symmetry currents, which are what these SU4 gauge fields are dual to. So in the pure n equals 4 theory, I have in SU4, whoops, global R symmetry. So do the simplest thing possible. Pick a U1 subgroup of that SU4 symmetry. And simply declare that to be your choice of what U1 electromagnetism is. Right? So at this point, somebody should say, which subgroup do you pick? What if you pick a different subgroup than I pick? And it will make almost no difference whatsoever. If we calculated the complete R symmetry current-current correlator, so these are the R currents, and these indices are running over all the components of the SU4 Lie algebra. The existence of that R symmetry is more than enough to tell you that the result of that complete set of current-current correlators, if you choose a sensible basis for your SU4 Lie algebra, is just proportional to a Kronecker AB. Which means if I now define my electromagnetic current to be some particular vector of charges dotted into these R symmetry currents, I guess I forgot my space-time indices there. The actual choice of what linear combination of these currents I pick to declare to be my electromagnetic current can't have any influence on the answer except for just one factor, which amounts to an overall normalization of this current. So I'm just going to pick a particular U1 subgroup that makes it as easy as possible to write down my analysis. And the only question to come back to at the end is how should you normalize the size of this current in order to make some interesting comparison, in particular in order to compare things to QCD. Let me just put off that one question of the overall normalization until the end. Okay, so if the only part of the bulk SU4 gauge field that's actually excited is an abelian U1 piece, then the only part of this square of the field strength that's going to be relevant is just the square of an abelian field strength. So the resulting equations of motion, right, are just ordinary Maxwell's equations for an abelian solution are just textbook freshman physics Maxwell's equations, except in curved space. Okay, so let's write them down. Right, go ahead, vary the gauge field. Half of Maxwell's equations is just this statement that the divergence of the field strength times a factor of root minus g equals 0. The other half of Maxwell's equations come from the Bianchi identities which I can write like that. Okay, now we've got to get a little more specific about which components we actually need to be interested in. And for that, put that here. I need to do one more bit, essentially, of kinematics. All right, what's the form of this correlator? What's it going to look like? Well, once I Fourier transform it, if I was actually looking at the retarded correlator, even though that's not the one I'm going to focus on, but it's related by the spectral representations, well, this is a correlation function of a conserved current. So if you dot, after Fourier transforming, if you dot the 4 momentum into this, it has to vanish. Therefore, the only terms that can appear have to have an appropriate tensor structure so that they're transverse. If we were working at 0 temperature, this would completely determine the resulting tensor structure because there'd be a single projection operator onto transverse 4 momentum that you could write down that would be consistent with Lorentz covariance. But we're not at 0 temperature. We're at non-zero temperature. So we don't have full Lorentz covariance. But what we do have is O3 rotation invariance plus current conservation. Therefore, there are 2 linearly independent structures that can emerge because I can write down I can build 2 different things. So what do I have here? I have something I will call a transverse projector, and by definition, what multiplies it is called the transverse photon self-energy. And this is a projector which is only non-zero if both indices are spatial indices. And then is proportional to a projection onto transverse 3 vectors. And this other term is a projector onto transverse 4 vectors, except to make things look nice, I'll just subtract the previous one. Okay? Now, this is the conventional definition of what are called these photon self-energies. And so the first point here is just that at non-zero temperature, there's 2 independent pieces instead of just having one the way you would at 0 temperature. There's a transverse and a longitudinal one, and this gives you the retarded correlator. If you take the imaginary part of the retarded correlator, that gives you the spectral density. And up to a factor of a Bose distribution function, that's the same thing as the Whiteman correlator that I said I want to calculate. So the net result is that the Whiteman correlator well, in particular, the trace of the Whiteman correlator is just related to the imaginary parts of these 2 self-energies. And I just wrote the trace. Oh, isn't that sad? It got erased. Not enough blackboard space. If you go back to the formulas I had on the board just a little bit ago for either photon emission or electrical conductivity, you'll see that it was sufficient to just calculate the trace of this current correlation function. So let's be efficient and let's just focus on that. Right, finally, look at this projector and notice that there's a denominator which is 1 over the 4 momentum k squared. So this term is singular on the light cone and is going to make this correlator singular on the light cone, which isn't physically sensible unless, of course, the longitudinal self-energy that's multiplied by vanishes as you approach the light cone. At non-zero temperature, a retarded correlator like this has no reason to be singular on the light cone, and therefore it must be the case that the longitudinal self-energy vanishes on the light cone. If I want to talk about photon production or conductivity, I showed that it's sufficient to calculate this correlator on the light cone. So that's good news. It means that I don't even need to worry about this term if I want to evaluate this at light-like 4 momentum. OK, so that reduces our problem to one of evaluating specifically the imaginary part of the transverse self-energy.
Is that supposed to be true at any temperature?
Yes.
At zero temperature.
Excuse me. At any non-zero temperature.
No matter how small.
Yes. OK, so back over to the gravity dual. I actually need to solve my curve space Maxwell's equations, but I'm perfectly free to pick a configuration that makes my analysis as simple as possible as long as it will allow me to extract that transverse correlator. All right? Well, that means I really want to look at a transverse electromagnetic wave in this bulk geometry. So let's look at a configuration where the Tx component of the field strength, which is, of course, what you mean by the x component of the electric field. Let's look at a configuration where this has a wave number that's pointing in the z direction. So the amplitude of this x component of the electric field wiggles as you move in z, and it has some frequency, but that's it. That's its only dependence on the 4 Minkowski coordinates. All right? But we're actually working in 5 dimensions. So this sort of plane wave is then going to be multiplied by some function of u, and that's what we're going to have to figure out. All right, let's assume that this is the dependence of all components of our U1 field strength tensor. But in fact, the only other component we're going to care about is the UX component. All right, why is that? Well, let's just start by looking at the Bianchi identity. All right, specifically apply the Bianchi identity where these 3 indices are, one of them is u, and then one of them is t, and one of them is x, because I want to find a solution with an electric field in the x direction. All right, so Bianchi tells me that this plus, let's see, which one do I want? dt f of xu, plus a third term, which would involve an x derivative, but by assumption, none of the fields have any variation in x. So I can forget about that third term. These 2 things equal 0. And I'm assuming that I have harmonic dependence in time. So a factor here is simply the same as minus I omega. So what this teaches me is that the u derivative of the x component of the electric field, and a prime is what I mean by u derivative, is the same thing as the ux component of the field strength up to a factor of frequency. Good. That's the information from half of Maxwell's equations. And now we just have to look at the other half. And what do we have to do for that? We have to look at this equation. There's a factor of square root of minus g. That was easy enough to write down once we just write out the metric. And what's significant here is I need components of the field strength, but with their indices raised. So that actually implicitly means using the metric tensor to raise the defining components of the field strength, which start with their indices down. But for the geometry, the ADS black hole geometry that I'm interested in, the metric is diagonal. So when you raise or lower indices, you're going to get factors of diagonal components of the metric, but you're not going to get any nasty sums. OK, so if you look at this half of Maxwell's equations, where that index b is x, then index a involves a derivative, and there's only two possible things it can be, either a u derivative or a time derivative. Excuse me. Yeah, that's right. Write it out. OK. So that's all you get. And lo and behold, here we have a relation that lets us express the ux component of the field strength in terms of the x component of the electric field. This is just the x component of the electric field. So take that, stuff it in down here, and we will have completely decoupled our equations and produced a single second-order equation for the x component of the electric field. OK, that's nice. Right? We don't have nasty coupled sets of equations. We now are just down to a single second-order equation. An ordinary differential equation, because we used our translation invariance in the form Minkowski directions. You can now go plug in the explicit forms of the metric components for the ADS black hole background. I'm not going to go through that bit of exercise, but I will write here just to show you the result. And it's really not that bad. All right. Some nice second-order equation of motion, except I have to tell you that I'm now going to use units in which 2 pi t is 1, and my ADS radial coordinate is sadly not the same as yesterday's. But is the square of yesterday's over UH. And the upshot of that is our function f of u is now just 1 minus u squared. Good. So what do we need to do? We need to solve it. with appropriate boundary conditions. And those boundary conditions are determined by the physics. So we need to solve this equation on the interval u goes to 0 to 1 by setting 2 pi t equals 1. I've made the position of the horizon u equals 1. And what can we say? Well, at the boundary, I have a second order equation. It has two linearly independent solutions. It's easy enough to look at that equation and analyze the asymptotic behavior as u goes to 0, which is a singular point of this equation. You do standard differential equation analysis, and any solution of this equation as u approaches 0 you must be able to write as some linear combination of two standard solutions. And there is a regular solution where you just have a straight power series in powers of u starting with the first power. So a solution that vanishes linearly as you approach the boundary. So that's a regular solution. And then there's an irregular, which I'm calling solution 2 for no good reason. And then there's an irregular solution, which has non-analytic behavior near the boundary. This solution goes to a constant, which by convention I'll choose to be 1. And has a term that looks like the regular solution times log of u plus further regular terms. And all these coefficients in the small u asymptotic behavior are completely determined by stuffing that form into the differential equation and demanding that it be satisfied. All right, that's the near boundary behavior. You can analyze the near horizon behavior similarly. And that's also a singular point of this differential equation. You analyze the local behavior, and you discover that the solution either behaves like the deviation from the horizon, 1 minus u, to an imaginary exponent, I omega over 2, or a complex conjugate. If you go and multiply this by an e to the minus I omega t and say, what do these solutions look like? You'll see that, let me get it straight here. This solution is ingoing to the horizon, and this solution is outgoing. In other words, if you look at wavefronts and you say, where do surfaces of constant phase move? Here, they're coming out of the horizon, and for this guy, they're moving into the horizon. Okay, well, we have a horizon. It's essentially describing a black hole. We're trying to describe sensible, real physics. It's okay for stuff to fall into the black hole. The black hole better not be spitting stuff out at us. So this is good. This is bad. Get rid of it. All right, in other words, we impose a boundary condition at the horizon that says stuff can fall in but can't come back out. That completely determines the solution to this differential equation up to just some overall normalization. It's a linear homogeneous equation. Nothing determines the amplitude yet. So the particular solution that satisfies incoming boundary conditions at the horizon will now, near the boundary, have behavior which looks like this for some very specific choices, well, a very specific ratio of the coefficients multiplying these two near boundary terms. So the physical solution we want is going to be a particular combination. And that particular combination I'm now just going to write near the boundary. I'm going to write as A of Z1 plus B of Z2. All right, so finding the ratio of these coefficients is non-trivial. But that's the important information for us. Why is that? Well, now we have to go back to saying, how do we actually get our correlator? So go back to the action. Let's just say the action. The only relevant piece of the action was the field strength squared. If you evaluate that action for a solution of Maxwell's equations, well, in the term, if I write it out in terms of a vector potential, if I choose to integrate this derivative by parts so that it ends up hitting square root of minus g times the field strength, that's what vanishes because we've satisfied Maxwell's equations. So on shell, I can rewrite the integrand as a total derivative. I can then convert the bulk integral into a surface term, and that's the resulting boundary action I'm going to care about. OK, since, as always, I'm running out of time, if you do that, what are you going to end up with? Well, I'll write it a little bit schematically, and then I'll write it a little more carefully. First of all, if I do a Fourier transform, I'm going to end up with factors of g. And then all I want to emphasize here is it's going to be a u derivative, which gives me a surface term because my boundary is at u equals 0. So the only piece of this I'm going to care about is the piece where I have a component of the field strength where one index is u. The other index, since I have an electric field in the x direction, I can say is just in the x direction because I can think about describing an x-directed electric field by simply having a time-dependent x component of a vector potential. So the only piece that's going to survive is a piece that involves this x component of A times fux. This we saw was related to the radial derivative of Ex from the Bianchi equation, what's written just above. Ax is going to be directly related to the x component of the electric field because we have harmonic time dependence, so up to some factor of minus 1 over I. OK, so when you clean that up a little bit, what you really get here is my function f, 2 factors of omega in the denominator, Ex prime, a little more carefully, uk, Exu, and minus k, evaluated in the limit u goes to 0. OK. Well, the boundary behavior of the electric field is in essence what I've prescribed by saying I'm turning on an external electromagnetic potential. But what I need here to evaluate this is the near boundary behavior of the radial derivative of the electric field. And that's where the analysis we did right here is relevant, because the boundary value is going to show up as the coefficient of this irregular solution that approaches a constant. But it's the regular solution that vanishes linearly, and therefore will have a first derivative which has a finite limit as you go to the boundary. So what's going to come out of this is really something which involves one factor of this coefficient b times one factor of a. A is just proportional to the boundary value that I'm turning on. And so what I really need to know is the ratio of b to a. OK. If you just turn that into words, well, I just turn those words into an equation, which I think I better skip over. There's a very simple direct relation between the transverse part of the photon self-energy, from which I can get all the physics that I talked about, and this ratio of coefficients in the near boundary asymptotics of the solution of our differential equation that satisfies the correct boundary condition at the horizon. Good. And I have minus 2 minutes? Oh, wonderful, wonderful. OK, so now you just have to roll up your sleeve and solve that ordinary differential equation, which sadly got erased. For arbitrary four momentum, by which I really mean for either time-like or space-like four momentum, so far as I know, there's no analytic nice formula for the solution of that ordinary differential equation, although you can, of course, solve it numerically. You can analyze its small momentum, small frequency, small momentum behavior analytically. I won't go through that. What I do want to say is if you're specifically interested in light-like momenta, which is the only thing we need to get out either photon production or conductivity, then in fact you can solve that equation analytically. And you can go through everything I just said. Two linearly independent solutions, find the solution that satisfies the physical boundary condition at the horizon. And that solution, well, has the factor, the oscillating phase of the near boundary behavior I told you about. If you also pull out just a simple factor of 1 plus u to the power minus omega over 2, and write the electric field as this times an unknown function and plug it in, clean up the equation a little bit, lo and behold, it's just the standard equation for a hypergeometric function. And so the solution is a 2f1 hypergeometric function with particular arguments which I don't expect you to instantly check, but there it is. All right, that's kind of nice. That is a formula for our solution of Maxwell's equations in the bulk with physical boundary conditions. You can now take this formula, you can look at its asymptotics near the boundary, you can extract these coefficients A and B, and in fact you can do it in a sort of clever way where you end up writing precisely this ratio in terms of a Wronskian of hypergeometric functions that's actually independent of u, so you can evaluate it wherever it's easiest to evaluate, and it's actually easiest to evaluate near the horizon. But let me just say the upshot is you can really just carry this out. You can work out what this ratio of B over A is and end up with a completely explicit formula for the transverse self-energy, which I won't write because the actual physics I wanted to get out only required you calculate the imaginary part of this transverse self-energy. That's what gave you the spectral density. So let me just go to that spectral density for light-like momentum. And this is just minus 4 times the imaginary part of pi t. And what is it? Well, it has our overall factors of nc squared. And with a little playing around with identities of hypergeometric functions, you can write it as the absolute square of a particular hypergeometric function. Actually as 1 over an absolute square. All right, why is that relevant? Well, spectral densities, ultimately, you go back to their definition, they involve sums of squares of amplitudes of some operator to create excited states summed over all excited states. From their basic definition, spectral densities of bosonic operators, of physical bosonic operators, have to be positive. Well, so it's reassuring to get a result which is manifestly both real and positive. I just misspoke slightly. There's a factor of omega here. I should have said spectral densities for positive frequency must be positive, and in fact, CPT tells you it's an odd function of frequency. Right, so it's omega times chi of omega. That's positive. Good. You can analyze the small frequency behavior of this because that's sufficient to get out the conductivity. So just by doing, easy asymptotics, I'll simply put, now let me go write it over here so you can see it. What you get out for conductivity all right, look at the small frequency limit. Go back to that formula I showed you initially. And out comes a nice simple behavior for the electric conductivity. Or, if you want, don't sort of think about electromagnetism and don't use that language. What I really calculated here was just a 2-point function of R symmetry currents. And I could just talk about that in terms of diffusion. The small frequency limit of that correlator is related to a diffusion constant for R charge. And in fact, there's a very simple relation between them, which you can infer from what I wrote on my first board. That's actually is called an Einstein relation because Einstein talked about the relation between diffusion and conductivity. That involves the susceptibility, which is an equilibrium thermodynamic quantity that I didn't calculate yesterday, but you can calculate using very, very similar techniques. And I'm just going to say when you put it together, you get a stunningly simple result for the R-charge diffusion constant, which is just 1 over 2 pi t. Okay, to wrap up, I wanted to show you some pictures. Take this result, stuff it into the formula for the photon production spectrum. What does it look like? And then I wanted to show you a little bit about what you can say about comparisons to QCD. Let's hope. I'm not seeing anything yet. Ah, it's there. Wow. Okay, so if you just take that formula I showed you with 1 over the square of a certain hypergeometric function and plot it, here is actually a plot of the result. Well, not quite the result. This is just that spectral density divided by frequency. That's the same quantity that appears in the Whiteman correlator. All right, so this is plotted as a function of rescaled frequency on the light cone. What can you say? Well, it's a perfectly nice smooth curve. The dash curves show both small frequency and large frequency asymptotics. That you can work out essentially by hand independently. It works well. There's nothing else very exciting to show about that. Just because it's a pretty picture, I want to show you that if you go and do the calculation I described for time-like form momentum, which is relevant if you want to talk about dilepton production. Here are pictures, slightly off the screen, but tough, for the transverse part of the spectral density or the longitudinal part, and it's their sum that's physical here, plotted as a function of, well, basically frequency plus wave vector on one axis and frequency minus wave vector on the other axis. So in other words, this edge right here is looking at it on the light cone, as is the opposite edge back there. Looking at it over here is looking at it as increasingly large time-like form momentum. So what do you see there? There is structure near the light cone. You have these wiggles that come down here. We could talk a little bit more about sort of what you can say about that physically. The thing I want to sort of emphasize most, though, is you look to see how boring it is in the middle here. Right? If you said, could there be, in some strongly interacting theory, interesting resonances, quasi-particles? How do you look for quasi-particles? Well, you look for bumps in spectral densities. In fact, some prominent physicists have talked about how in real QCD plasmas, they believe that there are significant bumps that influence physics dramatically at temperatures around, say, 2 times Tc. Well, this isn't QCD. This is n equals 4. In the limit lambda goes to infinity, the clear message here is you don't see any interesting structure. Right? There aren't any well-defined quasi-particles, at least as probed by this particular operator. Okay. 1 minute. Well, so I can't show you any better comparison to QCD in strongly coupled, in temperature ranges where we believe the relevant dynamics is strongly coupled, because we don't know how to do QCD there, which is why we're talking about n equals 4. However, it is perfectly fair to say how closely does n equals 4 super Yang-Mills mimic the properties of hot QCD in a regime where they're both weakly coupled. So that's different from everything I talked about today, but that's doing a actually difficult, more difficult than the strong coupling analysis I talked about today, analysis of this correlator in the weak coupling regime. That's something I happened to be involved in a handful of years ago for QCD. And with a little more work, you can repeat the analysis for n equals 4, and then you can compare. So these plots are trying to show you how the photon production rate, that's what's on the vertical axis here, scaled by alpha electromagnetic times t cubed, compares, except it brings up a very important point. How do you compare? The QCD result is a function of the alpha strong evaluated at the scale of the temperature. The n equals 4 result is a function of lambda, where lambda is a dial. You can make it anything you want. How do you compare? What value of lambda do you use to compare to QCD for some value of alpha s? The simplest thing you might do is to just equate alpha s, or in other words, the gauge coupling in QCD with the gauge coupling in Super-Yang-Mills. Of course, Super-Yang-Mills has a lot more degrees of freedom than QCD, right? They both have gluons, but in Super-Yang-Mills, you're now adding adjoint representation scalars, adjoint representation quarks, whereas in QCD, you just have a few fundamental representation quarks. So at equal values of the gauge coupling, in particular, there's a lot more electromagnetically charged degrees of freedom in n equals 4, given how we coupled it to electromagnetism. The photons that are being produced the way photons always are, by some charged particle getting jostled, getting accelerated, and deciding to radiate. There's a lot more things that can radiate in n equals 4, so if you compare at equal values of the gauge coupling, you see the n equals 4 photon spectrum dramatically above the QCD one. So, you compare here at photon energies of, say, 1.5 times the temperature, it's a pretty big difference. One of the lessons here is that's a bad way of comparing these theories. A much better thing to do is to focus on some physical scale that's relevant for the phenomena you're interested in and say, how do you adjust things so that physical scale is the same in both theories? And yesterday I talked about how to understand Debye screening lengths or other screening lengths in n equals 4, and the Debye screening length or screening mass is a very natural thing to focus attention on, because a lot of the physics that I've talked about in the weakly coupled regime really is sensitive to what's going on this Debye scale. If you make a comparison where those are equal, which means the 't Hooft couplings in these two theories are not equal and differ by, I believe, a factor of 4, then this comparison looks a whole lot better. The n equals 4 result is still a little bit above the QCD result, but now we're talking, well, for this sort of range of photon momenta that is potentially relevant to RHIC experiments, that's not such a dramatic difference. All right, since I have it up here, I'll mention that at weak coupling, what these curves really do is they rise linearly from 0 frequency, shoot up to a high, narrow peak, and then come back down. This fall off here is just the exponential Boltzmann suppression of very high frequency photons. The slope with which this rises is in fact precisely the conductivity. Okay, but experimentally, you're never going to be able to see structure of very soft photons. They're completely swamped by other boring things. Another thing you can do is to just look at the n equals 4 theory and compare the result at strong coupling to the result at weak coupling. Here is the energy-weighted photon spectrum compared that way. And the message here is good news for experimentalists. Namely, you get a lot more photons out in the strongly coupled limit than you do in a weak, well, in a not so weakly, but weaker coupling regime. All right, and again, for sort of experimental relevance, you care about that region here. So that's really good news, because it is difficult to actually measure the photon spectrum well enough. And what's really difficult is to separate different sources of photons that come out, because I've just talked about photons coming out from what you should think of as a hot, nearly thermal quark-gluon plasma. Real collisions are a lot more complicated. You have lots of photons that come out from decaying pi knots, and at sufficiently small momenta, that's a huge, huge source of photons that completely swamp things. You also have very high momentum photons that come out from processes that you think of as just ordinary hard scattering at the earliest stages of the collision, where you should really think about QCD in terms of partons. So photons from a nearly thermalized quark-gluon plasma are at best telling you about photons that you hope to observe in some intermediate range of energy. You're never going to get the right tail until you add it back on with perturbative QCD, and you're always going to have problems at small frequencies. But here's actually an early effort. This is over a year old, from somebody in, I believe it's the Phoenix collaboration, who used our results for the strong coupling n equals 4 photon spectrum, folded into a model of these other sources of photons, and showing that, you know, it does a pretty good job reproducing what they had for data at that time, using, I mean, tuning, frankly, the value of the temperature that he put into our formula. But the value that he needed to get a reasonable fit is actually a perfectly reasonable value given what's known about a variety of other observables in heavy ion collisions. So I better stop there, but that's my effort to actually say there actually is at least a little bit of connection between the theory we're talking about and real experiment. And that's amazing. Thanks.
Questions, comments?
Just two quick comments. I think it's worth noting that here we were able to isolate this equation for the gauge field because we focus like on the transverse mode. Otherwise, generically, it's not the case, and we will have to couple it. I mean, you have to consider the full coupling, like the Einstein's equations as well.
If what you're interested in is just the R symmetry current correlator, no. You have to consider the full set of Maxwell's equations and not just the piece that I focused attention on. But no, you don't actually have to do gravitational perturbations.
No, but I mean it back reacts to the metric, right? So you have to consider which mode you consider. So here you consider the transverse mode of the gauge field. So if you consider the longitudinal as well, then you have to consider the equations, the Einstein's equations as well.
We should talk about this
Okay. That was
privately,
first.
but no.
And the second comment was the correlator here is actually the on-cell action with the gauge field sort. This is logarithmic divergence. So I think, I mean, you cannot get away in that case like without adding the counter term.
So here, you are right, and I glossed over it. However, it wasn't a big cheat. So yes, when I said that the on-shell action just ends up giving me something that involved that ratio of B over A, I actually dropped a term, which has the divergence you spoke of. But in the resulting current correlator, that gives you a term which is simply a polynomial in 4 momentum. So if you Fourier transform it, it's just a contact term. And in particular, it doesn't have any imaginary part. All the physics I talked about just came from the imaginary part of the spectral density. So while what you said is absolutely true, it just drops out and doesn't affect anything I wanted to extract from this.
But contact terms in general are important, right? I mean, to preserve the wavelengths and so on.
Absolutely. And if you wanted to know what the full correlator was and not just the spectral density, then, well, as I said, it would add a contact term, and those contact terms are relevant and, as you said, affect word identities. It just doesn't affect this particular physics.
Any other questions? Your formula for that pi of t had b over a.
Right.
Now,
there's some curve in the omega versus k plane where a goes to 0, right? At quasi-normal mode frequencies.
Oh, so everything I talked about, you should have thought of the four momentum as being a real Minkowski momentum, right? If you now wish to think about analytically continuing, then yes, for certain complex values of that four momentum, you'll find quasi-normal modes which satisfy the physical boundary condition at the horizon without requiring a non-zero boundary value at the other end.
Right. And you should be able to read off like the diffusion and the conductivity just by knowing that curve.
That is absolutely true. So the way I describe to extract the diffusion constant or the conductivity is one way that happened to fit talking about calculating the correlator the way I wanted to. But you're absolutely right. If all you want to get out is those transport coefficients, you can actually do a simpler analysis. And one way of doing it is just what you said, of finding quasi-normal modes. Same comments apply to calculating viscosity. You can do it by really calculating that stress-stress correlator, but there are more clever techniques that let you specifically get the viscosity without working nearly so hard.
Okay, let's thank Larry again and go to